So now we're going to see some of the more crucial properties of logarithms. Again, they follow from properties of exponential functions that I'm going to write on the right-hand side. So one of the important properties of exponential functions, is the product rule, which is this. And there's going to be an equivalent product rule for logarithms. So we're going to deduce a rule for logarithms from this rule. Okay, so I'm going to do something that's kind of maybe awkward. I don't know. I'm going to let m be b to the little m, and n be b to the little n. Okay, so this means I'm going to call that big M and call that big N. Okay, now I'm going to rewrite each equation here in which are in exponential equations. I'm going to rewrite them in logarithmic equations. So so m is b to the m, so m is the exponent, so it's a log, to which I raise b in order to get m. N is the exponent to which I raise b in order to get n. Okay, so now I've rewritten those two exponential equations as logarithmic equations. And now I'm going to calculate log in base b of m times n. Why m times n? Because I want to use the product rule on the right and the product rule on the right. You see m and n are multiplied. So I take the log of m times n. So according to where I wrote, big M is b to the little m, right? So this is me using this. And little n, big N is b to the little n, like that. And according to my product rule, this is where I'm using it, product rule for exponents, this is b to the m plus n. Okay? And now I'm going to use the fact that if I have log in base b of b to the x, it gives me back x. Remember, that's because the logarithm and the exponential functions are inverse functions of one another. So this is sort of using f inverse of f of x is x. Okay, so that means this is going to give me back this exponent, right? This x. So this is m plus n. And m plus n, well, this is where I'm going to be using this. This is log in base b of big M, and n is log in base b of big N. So that means log of a product is the sum of logs. Okay, and it really follows from the product rule. So I haven't created any new mathematics here. It's just follows from the notation of logarithms and the product rule for exponents. So I'll just give you an idea. Let's say I want to calculate log of 15. Okay, I could break it up into logs of smaller number because the 15 is a product. It's 5 times 3. So that means, according to my identity, this is log of 5 plus log of 3. And I encourage you to check this out on using your calculator. So if you calculate log of 15 using your calculator, you're going to get approximately 1.176. Okay? If you calculate log of 5, you're going to get approximately 0.447. And if you calculate log of 3, you're going to get approximately 0.0699. Now, if you add those two together, you're going to get 1.176. Okay, so you can see using a calculator that it actually works. I can use this also with algebraic expressions. So if I have log of x squared minus 4, so it's log of all of that. If I factor x squared minus 4, let's say like that, okay, I get the log of a product which I can split into the log of two other algebraic expressions, but they're simpler now. So if you've got log of polynomial that can be factored, you can split it up into logarithms, a sum of logarithms of simpler polynomials. Okay, we've got another rule that's pretty important with exponents. It's the power rule. So b to the n to the m is b to the n times m. So in other words, we can multiply the exponents together. So for example, this you could write 5 to the 2 to the 3. That's the same thing as 5 to the 2 times 3, 5 to the 6. Okay, so there's a similar rule for logarithms. So log in base b of, let's say, n to the m. What does that give me? Now I'm going to use, just as before, big N is going to be, actually, I'm going to rewrite it here. So big N is going to be, N is going to be B, not the other way around. Little n is going to be B to the n. So that is equivalent to saying that n is the exponent. No, sorry, other way around. Big N is b to the little n. So n, little n, is going to be the exponent to which I raise b in order to get n, like that. Okay. So I will first replace here n with b to the n. So this is my first step. And this is raised to the m. So notice that now I can use my power rule for exponents. I didn't write it here, but I'm going to use the power rule. So this is b to the n times m, like this. Now, again, I'm going to use the fact that log in base b of b to the x is x. So this is just going to give me back n times m. Okay, which I will actually write as m times n, like that. And so I'm just going to flip around the order of the multiplication. And finally, I'm going to replace little n by log in base b of big N. And okay, so this means log in base b of n to the m is going to be m log in base b of n. So what does that mean? It means that, let's look at an example. If I have log in base 7 of 3 squared, what this property tells me is that I can bring the exponent in front of the logarithm. It's kind of a strange property of logarithms. It really just follows from the power rule. So this is the power rule for logarithms. So if there's log of something to a power, you can bring the power in front of the log. I'll give you another example. If you've got log in base 5 of 25, okay, let's do it in two ways. Okay, log in base 5 of 25. Well, if you think of 25, it's 5 squared, right? And using this property here, okay, we can easily see that the power to which you raise 5 to get 5 squared is just 2. Okay, so automatically we know this is 2. But let's do it in, using the power rule. I can bring the 2 in front. So it's 2 log in base 5 of 5. And log in base 5 of 5 is just 1. Like, to which power you raise 5 to get 5? Well, you raise it to the power 1. So you get 2 times 1, which is 2 again. Okay, so we see we get 2 in 2 different ways. Now, doing this property reminds me of something else I'll mention right after this other example. So if I've got a log of x squared, okay, that means I can bring the 2 in front. So it's 2 log of x. So I can do that. if I've got log of x plus 2's cube, I can bring the 3 in front like that. So it allows me to sort of simplify my algebraic expressions if I've got log of a power. Now, what the example I just did remind me of is that there's another property we can sort of list. We can actually add it if you want to. We can go back to property number 1 in your notes and add another one. You could also add this one, b to the 1. That's just b, right? That's pretty clear. So we can actually write this in using logarithms. It means 1 is the exponent to which you raise b in order to get b. So log n base b of b is 1. Okay, so maybe you can add an example for that. If I've got log n base 5 of 5, it's just 1. Okay, so that's a pretty obvious property. Okay, so we're going to look at another one. That's yeah, the last one actually follows from the previous two. So so for exponents, we've got b to the n over b to the m. This is b to the, actually I'm going to write m first, m and n. This is b to the m minus n. Remember, we can subtract exponents. For example, if you've got b squared over b cubed, this is b to the 2 minus 3. I can do that, or b to the minus 1, or if you prefer 1 over b. So there's a related property for logarithms. So if I've got log n base b of m over n, okay, I can write m over n as m multiplied by n to the power minus 1. I can do that. Now I can use the fact that I have log of a product. So here I'm going to use log of x times y is log of x plus log of y. I'm not using m and n because they're already being used before. So I'm using x and y instead here. So I can write this as the sum of two logarithms, like that. And finally, this guy, this exponent here, I can bring it in front. So this is what I'm going to use now. So here I'm going to use log of n to the m. This is m log of n, base b, whatever the base. This always works. So I'm going to bring the exponent in front. So that means it's going to change the sign here. And that's my last property. So if I've got log of a ratio and not log of a product, it's not the sum of the logs, it's the difference of the logs. Kind of cool. So I'll give you an example here again. If I've got log of 7 over 25, it's log of a ratio. I can write that as the difference of two logs. And you can check that this works on a calculator. Works completely. I can even like push this a step further. Log of 25, you see that's log of 5 squared, and then bring the 2 over. So this is using another property, right, where we can bring the exponent in front. And all this means that instead of evaluating this complex logarithm, I can evaluate the using logarithms of simpler numbers like 7 and 5. So obviously you have we can use this using algebraic expressions. So if I've got log of x plus 1 over x minus 2 squared, for example, you can write this as log of x plus 1 minus log of x minus 2 squared, okay, using this last property. And then we can bring the 2 in front of the logarithm, of the second logarithm, because it's an exponent for x minus 2. So then we've broken down this complex algorithm into two much simpler ones. This is going to be useful also for graphing like more complex logarithms. So what I'm going to do in the next videos is go over like examples where I'm going to be using all these properties that we actually saw. Now I noticed I didn't put numbers for all of them, so in your notes maybe you want to add more, so that we had property number 4. This is going to be property number 5 here. This is going to be property number 6. And we've got property number 7 here. The numbers are not important, it's just to show you that we've covered 7 of them.